Hello Internet, welcome to another tutorial in information theory and coding. Today we'll discuss systematic cyclic codes. In the previous tutorial we discussed non-systematic cyclic codes. Please understand, cyclic codes are example of a coding technique where some extra parity bits are sent along with the message signal so that its integrity is verified at the receivers. And in other words, if we want to detect and correct errors at the receiver, we must send some parity bits, some extra bits along with the message, so that the communication is more meaningful. In the previous video we also discussed the difference between systematic and non-systematic cyclic codes. In non-systematic cyclic codes, the parity bits are mixed up within the code word. They're not separated from the message bits. But in systematic cyclic codes, the message bits are going to be separated on one side from the parity bits. It is more or less like the linear block codes. So we have a question here. We'll do a question, and with this question we'll understand how the systematic cyclic codes are generated. So for a 7x4 cyclic code, the generator polynomial would be given something like this, and we need to find out code words for all messages. Now please understand that this is n and this is k. Time and again we discussed this, that n is the total code word length and k is the message length. So the parity will be n minus k, and in this particular case it becomes 7 minus 4, 3 bits of parity, 4 bits of message, and total 7 bits of code. Now the method of generating systematic cyclic code is pretty easy. I'll do it. By the way, for 4 bit message length we can have 16 different combinations ranging from 0 0 0 0 to 1 1 1 1. So for all the 16 different messages we can have different code words, of course generated by this generator polynomial. Now I'll take up one random message, for example 1010. Now step number 1 be to for 1010 we need to find out message polynomial, and we know the method of finding message polynomial. It will be x raised to power 3 plus this is 0, so x square will be missing, and then x, and then 1 will be missing because the LSB is 0. So this will be step number 1. Step number 2 will be to multiply mx with x raised to the power n minus k. So we get a term this. So here in this case our mx for this particular message is x cubed plus x, and we'll multiply it with x raised to power 7 minus 4. So in turn this will become x cubed plus x into x raised to power 3, or x raised to power 6 plus x raised to the power 4. Now why is this important? Because in step number 3 the parity for 1010 message will be the remainder of this term, m of x multiplied by x raised to the power n minus 1 upon our generator polynomial. So that is why I've already calculated this in step number 2. So now I have the task of dividing x raised to the power 6 plus x raised to the power 4 with the generator polynomial, which is x cube plus x plus 1. Now please understand this division is a long division method where we are going to use XOR method while subtracting. So I'll illustrate that. So in order to eliminate this, I'll use x cube. So this becomes x raised to the power 6 plus x raised to the power 4 plus x cube. So over here we do XOR. So the difference, the similar terms will get cancelled out. We get 0 here, and we are left with x cube. Now please understand, then we have the task of, again we'll do 1 and we get x cube plus x plus 1, and XORing will give me x plus 1. Now going backward in the similar fashion, we generated a polynomial. We have a term for x raised to power 0, so the least significant bit will be here, and this remainder is our parity. So we need to see parity for 3 bits, so we need to check it for x raised to power 0, x raised to power 1 and x raised to power 2. X raised to power 0 term is there, so put a 1 here. X raised to power 1 term is there, so put a 1 here. X raised to power 2 term is missing, so this is 0. So in other words, my code word becomes message plus parity, or augmentation rather. So my message is 1010 augmented by 011. So this is message, which is directly taken, and this is the remainder. And that's how it goes along. Let's take up another. This is 1, and I'll take up another message, for example 1110. So in case of 1110, mx will become x cube plus x squared plus x, and in step number 2 I'll generate m of x into x raised to power n minus k. So it will be x cube plus x squared plus x multiplied by x cube. So I get x raised to power 6 plus x raised to power 5 plus x raised to the power 4. So I get this thing in the numerator in step number 3, divided by my generator polynomial, and the remainder of this will become my parity. So let's calculate that. When divided by x cube plus x plus 1, I get x raised to power 6 plus x raised to power 4 and plus x cube. So XORing will do away these terms and I'm left with x raised to the power 5 plus x raised to the power 3. Alright. Then I'm left with the job of doing away with this x raised to the power 5 plus x cube plus x square, and XORing will eliminate this, keeping this as the remainder. Now because our parity is 3-bit, so checking it for x raised to the power 0, 1 and 2 terms, x raised to the power 0 term is missing, x raised to the power 1 term is missing, x raised to the power 2 term is there, so my parity becomes 1, 0, 0. If I augment this with my message 1, 1, 1, 0, this thing will become my entire code word. So my code word is message plus parity. So you can see the code word is separated from the parity in a systematic cyclic code, and that is how you populate the entire code word table for all the messages. Then you can find the minimum harming distance and so on and so forth. But that is how the procedure works. In step number 1 you generate the polynomial for the message. In step number 2 you simply multiply it with x raised to the power n minus k, and then divide it with the generated polynomial, find the remainder. That remainder is your parity. And I hope this tutorial was of help. If you like the content, give it a thumbs up, consider subscribing to the channel. I'll see you in the next video. You take care. Goodbye.